Kia ora koutou katoa, ko Dean Anderson toku Whenua. Yeah, thanks, Josh. And as Josh said, I'm going to be talking about looking at outcomes for Kia, given different management strategies over very large areas and over multiple decades. So it's a broad scale model, both temporally and spatially. And I want to acknowledge Mandy and all the work she's done in this area. Okay, oh, wrong screen, hold on, there we go. Okay, so in science, there are two main kinds of models. There are statistical models. And in those models, we input data and we estimate parameters that allow us to understand relationships, such as this graph here, which we estimate density given capture data and what influences density over time. Simulation models are another kind of models where we forecast out outcomes. And in these models, we input data, input parameters as well. We're not estimating them. And then we predict outcomes, such as whether or not it's going to rain tomorrow. In this talk, I'm going to look at how different management strategies over a large area of the South Island, shown on the left there, influence Kia over many decades. And so this is a simulation forecast model. But before we go there, it's important to understand how we use models such as this one to help inform decisions, given the plethora of different management strategies we could choose from. And so what I want to do here is discuss an important third kind of model, and that is a model that exists in our heads, because we are all modelers. We are constantly processing data from our five senses, and we're filtering out the vast majority of that. And those data that we retain, we have to make sense of so that we can understand the world. And really, what a model is just a simplification of the world so that we can understand the real world. So we're all very complex modelers. It's not just us sitting in offices working on computer code. So an example of a quantitative model in my head is when I go to the grocery store. I go through the aisles, I pick up stuff, and I put it in my cart and fill it up. And then I go to the checkout area and I look out over to the self-checkout area. And my model in my head quickly tells me, you're over 60 and there's far too much frustration and time over there. So that ain't gonna happen. So I then look over at the checkout queues and I quickly do a little data collection. I count how many people are in each queue, how much stuff they have, and how much or how efficient the checkout clerk is. Are they concentrating on the task, or are they talking with customers? And I do a little processing and I make a choice. And I start moving toward that queue, and my wife grabs my arm and says, no, this one. So she's got a different model in her head. Same objective, different model, different outcome, different prediction. And so this is all to say that we use this forecasting model to really test the models in our head, not to make decisions for us, not to determine what management should be, but to test the models in the heads of the operational managers who have to decide when and where we're going to deploy our limited resources. And so in using this model, if you agree with everything that goes into it, all the parameters, how we process the population dynamics and all that, but yet the outcome of the model does not align with your expectations, your model results in your head, you have to ask the question, well, what's wrong with my expectations? Or what's wrong with the model? Is it the parameters? Is it the way we're modeling the processes, and we create this dynamic where we adjust our expectations and we adjust the parameters, or we go out and do new studies to get better parameters. We adjust the model, and when those two outcomes begin to align, then we've got a useful tool to use to confidently make decisions. So it's not as if these models are intended to replace people. They're just there to test the expertise that we have. So this model is really designed to address the question of when and where do we apply management, and what do we do to achieve to our biodiversity outcomes, because we can't do everything everywhere all at the same time. As I said yesterday, we might have management zones shown in these colored polygons, and we may only be able to do 1080 in these limited areas, but what we really want is Kia increase population growth rate in this larger yellow polygon. And of course, outside of this polygon, there's Kia, but there's also predators out here that can immigrate or emigrate out of. And so given that we can't do everything everywhere all the time, where do we do where and when do we apply our resources? And so we developed a broad scale model that effectively superimposes a grid cell system over the landscape and does multiple processes at different scales. So at fine scale, we have survival, recruitment, predation, competition, habitat selection, and so on for the species involved, which are rats, stoats, and the prey species of choice. And then at broad scale, we have dispersal events, we have 1080, and we have masting or different forest productivity going on. And so we have this basic ecological model, which is fundamentally driven by forest or ecosystem productivity. And that influences rat dynamics, which we've heard a lot about in these talks. And rats then influence stoats. The more rats there are, the more stoats there are. And these three things, resources, rats, and stoats, all then influence our prey species. And in the case of this particular example, it's Kia. So that's sort of our base ecological model. But we can add to it additional dynamics such as prey switching. So when rat numbers are low, stoats might disproportionately start to target Kia, or the rat bounce effect that we've heard talked about in this workshop. And then there's a management ecological model. So we add in the human component, and we might do, as managers, we might do control. So we could do direct trapping of stoats, or we could do 1080, which affects rats, and then stoats eat the toxic rats. And this all has a knock-on effect on the prey. The added problem for Kia is that there is a lot of lead in the environment, and being inquisitive birds, they eat a lot of these. They go to these lead sources and consume lead, which can be fatal. And so one management application might be to remove the lead sources. If we just look at this spatial lead risk and how we handle that in the model, again, this is our principal area of interest in yellow, and this is the larger modeled landscape in red. And these yellow dots are dock huts that have lead on them. And then I've added a few around Arthur's Pass. These were provided by Kerry Weston. And so the spatial risk you can see is shown in the black layer, where light colors are high risk and that they decay spatially away from the lead points. So Kia's survival, if you look at this black line, this is the probability of survival with age. If there's, what did I do? There we are. Yeah, Kia survival. Let's look at the black line first. This is Kia survival with age. if there is no lead risk. So if there's no lead within its home range, or if there's no lead in the environment. Now this red line shows the probability of survival if an individual happens to have its home range centered on a point lead source. And so there's a substantial, the probability of survival decreases rapidly over time. And so the spatial lead, or the lead risk spatial decay, is shown here. So this is the probability of survival for a first year bird in its first year. And up here is if it happens to have its home range center on a point lead source, so near really close to a dock hut. And then that risk of survival over that first year will decrease as the home range center gets moved away from the dock hut. So that's how we're handling lead in this. And so effectively the lead risk area is shown in this red circle here around a dock hut with lead. So any bird that's got its home range center within this circle will be at risk of lead poisoning from this hut. So what I want to do is just quickly compare three scenarios to illustrate the model. And the first is a prescriptive 1080 application where we rotate 1080 every 3 years. So each of these management zones will get a 1080 application every 3 years. Maybe not all in the same, so we stagger them. So, but each one will get a 1080 operation every 3 years, regardless of what's going on with masting or rats. It's just a schedule. And the other one is reactive 1080. So there we're monitoring for masting events, which might trigger a 1080 event, or tracking tunnel surveys where we get greater than 0.2 or 0.25 tracking rates, 20 or 25% tracking rates. And then we take which of these two is the best. We determine which of these two is the best, and then we remove lead from the environment. And then we look at how Kia populations do after all of that. So let's look through some results here. And this is at Arthur's Pass. Let's just go back up one. This is this area here, this brown polygon area here. So that's where we're quantifying the results here. And so what we do is we burn in the model for, in this case, 40 years. And this is rat density on the y-axis in time. And this is present day here, although it says 40. This is present day, and this is when we start our new management regime of, in this case, prescriptive 1080 every 3 years. And you can see we really dampen down the rat maximum as well as the mean, but because it's just this regular treatment of 1080, we get this pulsed pattern of rats over time. And the stoat response is quite similar. We dampen down the maximum a lot and the mean, but we're still getting these big fluctuations in stoat density over time. And then Kia, we get from our initial seed density, we decrease down, and then it stabilizes a little bit, but continues to decrease at Arthur's Pass with this prescriptive 1080 regime. Now, if we do reactive control, reactive to mass and or tracking tunnels, we get a stabilization of rat density post the initialization of this new control regime, a reduction in both rats and stoats, and they're much more stable at a low level. But we're still seeing an ongoing slight decline in Kia. Although the decline is slightly less here, it's better. This is a better outcome than in the prescriptive one, but only marginally better. So then the next one, we're going to remove lead in addition to doing reactive and doing reactive to both mass and tracking tunnels. And what we see here is right after we remove the lead, we get a slight increase in the Kia population, but then it stabilizes, but this stabilization is very, very tenuous. There's a slight increase, but it's very, very tenuous. So we're not seeing a huge we're not with this regime, we're not seeing a big increase in Kia. Oops, wrong way. So now let's look at the Westland management zone, which is shown here. And this is interesting because it is, there's a lot more podocarp down here versus a beach dominated system up in Arthur's Pass. And the Kia, the stoat numbers are just so high in the model that the Kia numbers plunge, and they stabilize after we apply some lead. And what's interesting is that they don't seem to go to extinction. And I'm not quite sure what's going on there. That requires a little bit more investigation. But I think what's happening is that there are these spatial patches in the landscape where stoat numbers are very low to absent, at least temporally, where recruitment can happen and adults have a lower probability of predation by stoats than chicks. And so it's the spatial patchiness of stoats and Kia that is allowing for persistence, but at a very, very low level. And there's a very small increase going out from the onset of control going out. So let's look at the principal area of interest. So what's going on in this entire area? So if we quantify rats, stoats, and Kia within this yellow polygon, and it's much the same story, really, but definitely not an increase in this case. There is a steady decline of Kia going on here. So let's those are my main results. And to summarize, we have this model that allows us to forecast biodiversity outcomes over very long time periods given a management strategy. And one thing I want to emphasize here is that there's no definitive run or answer from this model. The model's designed to test hypotheses or test management scenarios and challenge the models or the expectations that we have given those different management scenarios. And then given the lack of alignment between our expectations and the model outputs, we need to challenge ourselves to alter how we think about these systems or look at the model and try to modify it. That may mean collecting understanding our parameters better or modifying the processes. So what we found is that reactive management and removal of lead led to a very tenuous stabilization of Kia population in the management zones, but we saw a slow decline across the entire region of interest. And that's because we're not controlling in large areas of the full area. There's a lot of uncontrolled area where predators aren't controlled. So these results, I've made a strong point of saying that we use this model to test our expectations. And to me, I'm these results do not align with my expectations. I was certain that if we applied the level of control that we're applying now and removed the lead, that we would see a steady increase in the Kia population over time. Maybe not a rapid increase, but at least a noticeable increase. So the number of 1080 operations per year across all those management zones was about 1.75 operations per year across the region. So what would it take to get consistent increase in Kia population? Clearly not more 1080. We can't throw more 1080 at this. Number one, it's not feasible. We're already probably doing more operations than is affordable or logistically feasible. And number two is we're already reacting to both mass and tracking tunnels. And so if we were applying more 1080, we would just be throwing 1080 at very low rat populations, which would have a minimal impact on the stoats. So it wouldn't help. So how about aerial PAP or other predator-specific toxins? Those, well, I don't know about those, but that may be a big hope for us in the future. We may need to refine the model. We may need to refine the parameters with scientific support. We can't just go and change parameters so we get the outcome that we want. So for example, the rat bounce seems to have a big impact because rats bounce back so fast that allows stoats to come back so fast. The prey switching has a pretty big impact as well. The rates of predation on the different Kia age classes. And I think I'm really out of time. So I'm going to finish there and just make my acknowledgments. And I just want to say that if you don't like the results of this, that came out of this model, the people listed on this slide are partially to blame. Kia ora.